For Lesson 2, Properties of Area, we're going to take a deeper look at area in terms of transformations, as well as finding areas of the shaded region. Furthermore, we will explore sets. In this opening exercise, we're asked to calculate the area of each triangle. They are both triangles, so we need to know that the area formula is equal to the base times height divided in half. Go ahead and calculate that now. Remember to press pause. See if you get the same answers as I do. I'm just going to write the formula at this point in time. Area is equal to base times height divided in half. Since the two triangles have the same dimensions, the area is calculated to be 52.92. So part B, circle the transformation that, if applied to the first triangle, would always result in a new triangle with the same area. So the ones that apply are a translation, a rotation, and a reflection. If you recall, these are the three that preserve lengths of the sides of anything, a polygon, as well as angle measurement. These are known as rigid motions. So preservation again is of length and angle measure. And as we know, dilation is infamous for not preserving length, and as a result, it is not considered a rigid motion. So that's the explanation. So the three are rigid motions that preserve length as well as angle measure. Dilation, of course, does not preserve length. However, it does preserve angle measure, so it's excluded. Now we will get into calculating the area of shaded figures, and in some cases, depending on the circumstances, you will either be adding areas or you'll be subtracting areas, depending on how they look. In this case, we'll be adding areas because you need to take a look at this not in terms of one entire diagram. It's a summation of 3 polygons. So if you look in the middle here, we have a rectangle, so you have to remember the properties of a rectangle, and then we have 2 triangles on the end. So we know the formulas for each one of those, and using the dimensions that we're given, the first thing I want to do is find the area of one of the figures. I'm going to go with the rectangle first. Then you're going to find the area of the 2 triangles, and then you're going to find the sum of all 3. So those are the list of steps. So I can see that there's a dimension of 3 right here. That's going to serve as the width of my rectangle. So I have 2 dimensions now, 7 and 3, and the area formula is base times height, or length times width in this case. So the area of the rectangle is 7 times 3, which is 21. The area of the 2 triangles, well, let me find the area of one. And as you can see, they're congruent triangles. They have the same dimensions. So area formula for a triangle is half the base times height. And since I have this value for 3 here, I can slide that over to be the altitude in this triangle. So I have now my base, which is 3, and I have the altitude as 3. So that's 3 times 3 divided in half. So 9 divided in half is equivalent to 4.5. I want to double that in order to represent the area of both triangles, being that they have the same dimensions. So that's equal to 9. And then we're going to sum these two values together and get the total area to be 30. And it's 30 square units, whatever the units may be. So for the second example, as you can see, we have a diagram within another diagram, and we want to find all this gray area here. So the first step is to find the area of the rectangle, which is the larger figure. So I'm going to put larger figure. Find area of larger figure. Second step, find the area of the triangle, the smaller figure. And then we're going to subtract the two values in order to find the area of the shaded region. It's the amount that's left over between the two areas. So in following this list of steps, what I have here in terms of a diagram, my larger figure is the rectangle. I'm going to find the area and subtract the area of the smaller figure, the triangle, and then I'll get the area of the shaded region. So let's start with the rectangle. So we know that the area formula is length times width, and that means it's 21.6 times 12, which gives us 259.2. And the area of the smaller figure, which is a triangle, is 1/2 the base times the height, and since it's a right triangle, we have the base and height as 9.6 and 7.2. So the product of those two divided in half is equal to 34.56. And we subtract these two values to get a difference of 224.64, which is the area of the shaded region. Now we're going to venture into the world of sets. And here's some vocabulary that you should transfer into your composition notebooks. Perhaps you could cut this grid out and transfer it into your composition notebook, or just copy it via writing. That's up to you. Okay, so a set is a well-defined collection of objects. These objects are called elements or members of the set, and it's written or notated with brackets. Then we have a subset that's always taken from the set. So a set A is a subset of set B if every element of A is also an element of B. the way in which we indicate a subset is like this, and we're indicating that set A is a subset of B. So this is the symbol for that. A union of subsets A and B is the set of all objects that are either elements of A or of B or of both. Okay, so I have to tell you that the way in which they wrote this is not correct. So a union of two subsets are elements of both. You have to have all or nothing. So it's not either A or B, it's both. And this is the way we represent that. Subset A is a union of B. That means all of the elements for both subsets are merged into one. An intersection of subset A and B is the set of all objects that are elements of A and also elements of B. This is not correct. Okay, they are not all objects. They are only the shared objects. Shared. Okay, I've never seen this depiction before, but this is the way intersection is. It's an upside down U. Okay, so a U represents union, upside down U represents intersection. So in these exercises, we're given sets A and B, and we want to find the union of A and B. So that's all of the elements. We're not going to repeat any, so that means we're not going to write it twice if we see it there twice. We're just going to represent it once. So the union with all of them merged is 1, 2, 3, 4, 5, 6, and 8. The intersection is what they share. So that's 2 and 6, which, by the way, these create subsets in their own right. So is A a subset of B? No, because all the elements in A are not in B. And is B a subset of A? The answer to that is no, because not every element in B is also in A. The two things that are missing in A that are in B that would make it a subset are the numbers 2 and 8. Okay, so for number 2, we're given D and E. Those are sets that we're going to find the union of. So that means that's all. Those are all the elements. So 1, 2, 3, 4, and 5. The intersection is the shared. So that's 1, 3, and 5. Okay, so is D a subset of E? So clearly it is not. And is E a subset of D? Well, we have 1, 3, and 5 in E, 1, 3, and 5 in D, so yes, it is a subset of D. So now in terms of area, we're going to apply the thought or notion of intersection and unions. So we have a 2 by 2 square region as labeled S subscript 1 and S subscript 2. And they meet at the midpoints of the sides shown. So since they meet at the midpoints, which I will designate here, it looks to be about 1/4 of the square, of each of the squares, that is. And if I know that these are 2 by 2, then this has got to be 1 by 1. So the area of a square is side square. So the area of the smaller square of the region that they share is a 1 by 1. So it's 1 times 1. So S squared is equal to 1, which is the shared region that we're looking for, otherwise known as the intersection. Therefore, area is equal to 1 square, which is equal to 1. So now we want to find the area of the union of the two squares. So what we're going to do is find the area of each of the square, which they're identical squares. So area is side square, and we know that it's a 2 by 2, so 2 square, that's equal to 4. Multiply that to 2 to represent both squares, in which case we get 8. The union is we take the whole, subtract the 1, and we get 7. So the union is equal to a difference of 7, and the intersection is 1. So we have two triangles here, ABC and DEF, and one overlaps the other. Okay, so the base figure ABGEF is comprised of segments of the following lengths. So those are labeled in the diagram already. I see that DC is equal to 3. I do not see that labeled, so I'm going to put that in right now. And we're asked to calculate the area of the entire figure, ABGEF. And we need to explain how we determine the area. I was also given that AD is 4. I do not see that labeled. And CF is 2. So visually you have to recognize or see that you need to find the area of the larger triangle. So that's ABC. And you also need to do the same for the smaller triangle, which is DEF. Notice that they share this region that's colored a little bit darker, okay, which is DCG. We're going to find the area of ABC, this one right here. We're going to find the area of DEF, which is this one right here. And then we're going to have to subtract the area of DCG. So I'm going to have to find the area of this smaller triangle that I've highlighted in red in the diagram. Because it's counting, we don't want to count it twice. And we're going to find it in both, basically, using the area twice, and we're going to subtract it, if you can make any sense of that. So both triangles are including that little area, and we only need to count it once. So for the first one, the area of ABC, we know is 1/2 base times height. So the base is 7, so that 4 plus 3, and the height is 4. So that's 28 divided in half, which gives us 14. The area of triangle DEF, we know DF to be 5, and the altitude known as the height to be 2. So that is 5 times 2 is 10, divided in half is 5. And then for the third step, I'm going to find the area of triangle DGC. So that's 0.9 times 3 divided in half, which gives us 1.35. Okay, so we're going to take 14, 5, and subtract 1.35. to get a sum and difference of 1765. So here's an important discovery. The area of the union of two regions is the sum of the areas minus the area of the intersection, so that the overlapping part is not counted twice. So in order to answer this question on how we find the area of polygonal regions that we do not have formulas for, you're going to extend them or break them up into polygons that we do have formulas for. So we want to try and make things into triangles, rectangles, squares, anything along those lines. So for the arrow, I can draw a line right here and get a rectangle, or perhaps even draw an altitude here in order to get two right triangles. In this case of the trapezoid, I can draw a line here and get a nice right triangle. I could do the same over here, get another right triangle, and I also have this rectangle in the middle. And then you could find the areas of those figures and add them up. When we get figures like the ones down below, we may want to draw pictures on the outside of the figure and then subtract. See how I get a right triangle there? I can extend that out here, drop a perpendicular here, and we get a nice four-sided figure just like that. So what you would do is find the area of this four-sided figure, okay, and either this would end up to be a rectangle or a square, and find the area of all the little triangles, so 1, 2, 3, and this fourth one down here, and subtract their sum from the area of the four-sided figure, the quadrilateral, and you would end up with the area of this unique looking polygon. So this last one is very odd looking. So what I would do is make a right triangle here, a right triangle here, and maybe draw a line down here. So you're going to have the combination of subtraction. So we would subtract the areas of these two triangles, and from the area of this whole entire quadrilateral that's in blue, and then find the areas of these two triangles on the ends and add them to that area in order to get the whole entire shaded region, which is this odd figure here along with these triangles.